Hello everyone. In the last video, we talked about the definition of groups, and we also showed some examples about groups. But in this video, I want to talk about several important properties about groups. But before we doing that, let's look at the notation of a group. You can see in this proposition, it used G to denote the group. So it says G is a group. But according to the definition, we know that a group is actually a ordered pair looks like this. It includes set G and a binary operation star or other symbol. But for convenience, and if there is no confusion, we usually just use the letter of the set to denote this group. So we can say this is group G, and we omit this operation symbol. And so this G group is same as this notation. Okay. Now let's look at the properties about the groups. Here we can see there are 5 properties. Let's look at them one by one. For the first property, it says that the identity of G is unique. So it means there is only one identity in a group. And we can prove this. Typically, when we want to prove something is unique in a set, we just assume there are 2 elements in the set with the same property. Then we prove that those 2 elements are actually the same. So we can do this here, and so we just assume E and E prime in the set in the group G are both identities. Okay. Then what we want to do is to prove that those 2 identities are actually the same. In order to do that, we can do the operation between them, and it looks like this. And let's see what can we get. And if we do the operation like this, because we know that E is the identity of the set of the group G, so by the definition of a group, we can know that the result should be E prime itself. Then, similarly, because this E prime is also an identity of the group G, and by doing the operation with the element E, we can get the result is also E. So from this, we can see that we actually get E equals to E prime, and this is what we want. So it means no matter how many notations in these groups are the identities, they just a different notation of the same identity, because they all are the same. So this means that the identity is unique. Okay. Now let's look at the second property. For the second property, it says for each element in G, the inverse of A is uniquely determined. So this is similar as the last one. We want to prove that the inverse is unique. And also we can use the same method, which we assume there are 2 inverse of this element A. Then we prove that those 2 inverse are the same. So proof. We assume here we don't use the notation A inverse like this. We just say we just use B and C in G such that B and C are the inverse of the element A. Right. Then we just show that B and C are equal. So to show that, let's look at those inverse. For example, let's look at the B. What is B? Because we don't have too much things we can use, we don't have too much properties or definition we can use. And here we looks like we can only use the property about the identity. So B is just the B star E is an identity element in G. So we get this. And what is the identity element E? The identity element, we can separate it into like this, A star C. This is because C is the inverse of A, so A star C is the identity. So those two expressions are the same, right? And here we have the operation among three elements, so we can use the associative law. And this is just equal to we do the operation between B and A at first, then do the operation with C. And here, because B is the inverse of A, so this B star A is the identity, so we get E star C here. And this is just C itself because E is the identity. Now we can see from B we get C, so B equals to C, and this just shows there is only one inverse of the element A, so we prove that the inverse is unique. Okay, number 3 says that the inverse of A equals to A itself for any element A in the group G. To prove this, at first we pick any element A in the group G. And because this equation is about the inverse of A, so we can at first let B be the inverse of A. And because B is the inverse of A, by the definition of the inverse element, we can get the equation A star B equals B star A equals to the identity E. And this is get from the definition of inverse element, and because B is the inverse of A. And similarly, this equation also says that A is the inverse of B, right? Because B is inverse of A, so A is also the inverse of B. And A is the inverse of B means that A equals to the inverse of B. And what is this B? This B here, it is just the inverse of A, and we substitute this this definition to here. We get the inverse of A, then inverse, and here we get the equation we want. So we proved this. And this property shows that the inverse, if you do the inverse 2 times, you just get the original element. And also, if you do the inverse for even times, you also get the original element. Okay, then we can talk about the number 4. We can look at this equation. It says that when we do the inversion on the operation of 2 elements, it can become like the right hand side like this. It will become the inverse of B star the inverse of A. So it means when you do the inversion over this operation, the order of the operation will be switched, and then each element will be inversed. Let's prove this. And to prove this, because we can see the left hand side is the inverse of this thing, and we can go with the definition, which is if right hand side is the inverse of the A star B, then it is similar to say the A star B star the right hand side it equals to, if we switch the order, okay, A star B, and those two are all equal to the identity E. Okay, so this is what we want to prove. And to show this, let's go one by one. To show, we can show the first part is equal to the identity. So let's say for this, to calculate this, we can see if we treat this A star B as one element, then this is just the operation between three elements, and the operation for the two elements at first. So we can use the associative law, which this will be equal to A star B, then star, we do those two at first, B inverse, and then we star A inverse, right? Okay, let's look at this. And here, inside this bracket, we can see this part is also the operation between three elements, and we can use the associative law again. And here, this part becomes to A star B inverse, then do the A inverse. Okay, and here we can see this one is B star B inverse, which is the identity, and A star, the identity, is A itself. So the first part becomes to A, and the second part is, we just copy this part, which is A star A inverse, and this is just the identity, right? And similarly, we can prove this part, this one is equal to the identity. The steps are the same, so I don't write here, but you can try it. Just use the associative law for like 2 times, you can get the identity. So we can say this is proved. And then for the last one, number 5, it says that for any A1, A2 until AN elements in the group G, the value of A star, A2 star, A3 until star AN is independent of how the expression is bracketed. This is called the generalized associative law. And this means that for the operation between n elements like this, no matter how you put the bracket in this calculation, or equivalently, you can say no matter which part you do the operation first, the result will always be the same. I will not prove this in detail, but the idea is very simple. I just show you an example. So example, let's look at like 5 elements in the group G. If we have A1, A2, A3, A4, and A5 in the group G, and we do the operation like this: A star 2, A3, A4, and A5. and then we can put the bracket like in any way we want. For example, we can do it like this. We do the A1, A2 at the first, and A3 and A4 at the first, then do the operation between the results of those two parts, and then do the operation with A5. And also we can just copy this. Also, we can put the parentheses like this, or like this. So no matter how we put the brackets, we get different expressions of these operations, and the property just says that no matter how you put the parentheses, or no matter which part you do the operation first, the result will always be the same, which means for example, for those two, their result will be equal. So the idea to prove this is to say that, to show that no matter what format you have, you can always transfer them into this form, A1 star, A2, 4, A5. You can always transfer them into this form. So which means you do the operation of the first two at the beginning, and then the result is operate with the third one, and then the result is operate with the fourth one, and goes on until to the last element. So because this one can be converted into this form, this one can also be converted in this form. So it means any form of the expression are the same. So this is number 5. Okay, so those are the 5 properties. They are very useful in your calculation about the groups. So you can do some practice on those properties and get familiar with it. And this is what I want to talk about in this video, and see you in the next video. Thank you.